Okay, welcome back. I'm going to cover points and vectors today. Most of this is review. Here's a Cartesian plane on the left. Super convenient way for locating points. For example, this point B is 1 unit to the right and 1, 2, 3 units up. So we can write its location like this as an ordered pair, 1, 3. And this point A is 3 units to the right and 0 units up. So we can write it like that. Similarly, this C is 1, 2, 3, 4 units to the left and minus 2 units down, like this. Great. And that's how we locate points. And once we have some points, we might want to know the distance between them. So if I connect A and B with this line segment, really the distance between A and B is just the length of this. But how could we find that? Well, the picture kind of suggests a way forward. I could imagine completing a triangle here, a right-angled triangle, and then this forms a hypotenuse, and to find the length of that hypotenuse, we just have to apply the Pythagorean theorem. So we need the length of this side. Well, considering A is at a height 0 and B is at a height 3, this would just be height 3. In this horizontal distance, A's 3 units over, B's only 1 unit over, so if I look at the difference of them, that's just 2. So to find the length of this side, I just need to take the square root of 3 squared plus 2 squared. Okay, and that will give me 9 plus 4, and that's root 13, which I'll leave as root 13. I don't want to appeal to decimals. I don't want to do what they do in high school and simplify the radical. Root 13 is a perfectly fine number, and that represents the distance between A and B. Okay, let's move on. Let's move on here. We can do something similar with any of these points. We could just locate them on a grid. 1, 2. So A would be here. B would be at 3, 3, 3, 3, right here, like that. Then to find the distance between them, we could just complete this this triangle, this right angle triangle. Look at the length here and the length here. And if you look, this horizontal length, for example, is just the difference between the x values of B and the x value of A. So here it would be 3 minus 1. And over here, the vertical distance is just 3, the height of B, minus the height of A, which is 2. So to find the distance between A and B, which we might write as the distance between A and B, that's just this like that. And you notice that these are squared. So it doesn't really matter if I subtract the B coordinates from the A coordinates or the A coordinates from the B coordinates, right? I could have equally well done this, and I'll get the same number. Okay? Let me just finish that calculation. That's just 4 plus 1 square root of 5. And again, I'll leave it as the square root of 5. Okay. Let's look at that third one right there. And I'm going to appeal to this GeoGebra, which is another free online graphing calculator, similar to Desmos, but this one allows us to plot in 3 dimensions. So here I've got 2 points. These are the points from this question here. So A and B. They're floating around in space like that. Now to find the distance between A and B, I can connect them by a line segment, and I just have to find the length of that line segment. Well, it's going to form a triangle if I look at this kind of vertical line here coming from A and connecting it to a horizontal one coming from B. You can see that forms a triangle. And to find the length of this hypotenuse, I just need to find the length of this side and the length of this side. Well, this bottom length is actually another triangle. It's the hypotenuse of another triangle. It's the triangle formed by looking at this line and that line. So really, we have this kind of image here. Ultimately, we're trying to find the length of this hypotenuse, and to do it, we could just find the length of this, the length of this, and the length of this. Okay, that might seem pretty complicated, but in practice, let's take a look at what that is. The length of this side is just the difference between the, this green axis, we could call it y, for example, or, I'm going to call it y. So these middle components, B is located at 0, -2, 1, and A is located at 1, 3, and 4. So this here is just 3 minus 2. That's the length of this side. The length of this side is just 0. Well, let's take the components from the A point and subtract those from the B point. Okay, so that just gives me length 1, which you can actually kind of see if I were to rotate it, you could see. And then this difference is just the difference in the height. So this would be 4 minus 1. Okay, so that gives me 3. This gives me 1. This gives me 5. So if I want to find the distance between these 2 points, watch what it looks like in practice. I just have to kind of apply a higher dimensional Pythagorean theorem to these guys. So I could take the first one I have here, square that, plus this one over here, let's say, square that, plus this, squared. So that just gives me the square root of 1 plus 25 plus 9. Square root of 35. Okay? And again, I'll just leave it like that. When you're doing distances, they always work out to be some root of something. So there's no real sense in trying to change that number. Just leave it as square root of 35. That's going to be this here. Okay? But what I want you to focus on is it's really just an application of the Pythagorean theorem. You just take the difference in the x coordinates, if this is the x-axis, the difference in the y coordinates, if that's the y-axis, and the distance in the z coordinates, this vertical distance. Okay, let's go back. I'll be leaving these problems unsolved for you so that you can try them on your own. You can discuss them with your colleagues, and you're absolutely welcome to come to me and discuss them as well. So you could try finding the distance between these 2 points floating around in 4-dimensional space. I don't have a 4-dimensional graphing calculator, but you could imagine how that might work and try to apply the generalized Pythagorean theorem to find that distance. Okay, a few other points to raise here about the Cartesian plane. Here's an equation. If I were to graph that equation, what would it look like? Well, it would have to be fixed at x equals 1, but you notice that there's no y variable involved. So that means that y could be anything. It could be 1, it could be 2, it could be, -3. It could be anything. So if I were to look at all those possible y values, oh man, that is the least liney line I've ever drawn. But you can imagine there's a line that goes through x equals 1, and that's this equation. Okay. So if I were to write out y equals 1, what would that look like? Well, it doesn't stipulate what x has to be, so x could be anything so long as y is 1. It's going to give me that. Okay, we could also appeal to Desmos to have a bit of a nicer graph, so I could draw it like this. You'll notice it's a perfectly vertical line, and let me do this. There's a horizontal line at y equals 2. Again, these equations, they don't, for example, this one, first one, x equals 1, doesn't stipulate what y could be, so y could be anything. That's what gives us this vertical line. The second one doesn't stipulate what x has to be, so x can be anything so long as y is 2. That's that horizontal line. Great. Moving on, you've probably encountered vectors before in some way. If you think about how vectors are written, they're written just like points are. If you look down here, v equals 1, 3, that's a vector in 2 dimensions. This is a vector in 4 dimensions. But you notice, they're actually written the same way that points are. Okay? And for my money, there's no real difference between vectors and points. The real difference is a conceptual one. We want to think of forces, for example, as having a direction and a magnitude. And that's where vectors come in. But like practically, mathematically, these work the same way as points. So I don't distinguish them because they work really the same way. If you want to find the length of a vector, you would just take the point at which it starts and the point it ends and find that distance. Okay, so let's look at that a little bit more. We could draw, for example, these points, 1, 1, and 3, 2, 1, 2, 3, 2. So if I treated these ordered pairs as points, that's what it would look like. If I wanted to treat it as vectors, I might want to do that just to indicate that they're vectors. I might draw some arrows out from the origin to them. Now I want to add them. We can do this very simply by just adding the x components together and adding the y components together. Okay? That's going to give me something like this here. 4, 3. 1, 2, 3, 4. 1, 2, 3. So that gives me this new vector. Okay? You might have seen this at one point, that if I were to treat this as a parallelogram, so then this side is parallel and has the same length as this side, and similarly this is parallel and of the same length as this side, then that far vertex is the sum of those two vectors. Okay, like that. Oh, that's the worst. Sorry about that. I'll draw straight lines on Desmos. Okay, so very simple, you just add the components together. Same for when you're subtracting them, you subtract the components. Before I talk about this, I just want to talk about these brackets that I'm using. Okay, you might, though you don't really need to, denote vectors with these kind of sharp brackets like that. You could do it round as well, but you'll notice, like in this yellow box on the right, that some authors choose to write vectors like that to distinguish them from points that have parentheses rather than brackets. But you'll notice here, I'm intentionally switching between the two forms, ultimately because it doesn't really matter in most settings, but you just have to be aware of the context. Maybe in a physics class they would like to distinguish points by putting parentheses rather than brackets, something like that. Okay, now let's talk about this. This is a scaling of a vector. And to look at it, let's go back to Desmos, and we'll write out a vector. We'll put down that vector, 1, 3. You just simply type it in like this. There it is, that green point sitting here. And why don't we just naively put in that coefficient and see what happens? First, can you anticipate what might happen? Let's try this. So it went from 1, 3 to 2, 6, kind of not surprisingly. 2, 6. And it ended up at that point. You can see. Okay. So this is generally what scaling does. If I put a little slider here, and I change it, you see it's 1 right now, so it's as if it doesn't have a coefficient. If I increase it, you see what happens. I increase where the point is. If I put it just at 2, I end up on that black point. Okay? And if I put 0 here, not surprisingly, it goes through the origin. So you can see the effect of multiplying through by a scalar. The good news for us is that it's very easy to do that. You just simply multiply each component by that number. Okay, I am going to leave this for practice for you as well. Again, try these problems, talk to your colleagues about it, talk to me about it. Okay, one last topic here. We want to think about vectors, but in terms of their direction and not necessarily their length. So you might want to remove their length. Just have a length 1 vector pointing in the direction of the vector that we're given. How might you do that? Well, you could simply find the length of the vector and divide through by it. So let's practice finding the length of a vector. So my vector is v. To find the length, we first write it like this, a pair of vertical parallel bars on either side of the v. And not surprisingly, we find that length using the Pythagorean theorem. Okay, so this is the square root of 50. That's the length of v. Now, if I want to what's called normalize this, change the length of the vector from square root of 50 down to the length of 1, all I have to do is divide through by the length. Okay, so this would be 1 over the square root of 50, like this. Okay, this new vector is called a unit vector. It's called a unit vector because it's of unit length. If I were to calculate the length of this vector, I would get 1 back. Okay, and you can try that on your own. You can try calculating the length. I might rewrite this a bit just to help you out, to suggest a way forward. I could rewrite it like that. Now you can try on your own finding the length of this vector, and you should get 1 back. So this whole process of taking a vector and then scaling it back so it has a length of 1 is called normalization. And this is useful because it gives us a vector in the direction of v, but of length 1. And we'll see why that might be useful later on. Okay, so here I've got some practice for you, just some normalizing practice. And again, I say find a vector that points in the same direction as the given vector, but has a unit length. Okay, so it's a little bit of an extension of what we've already seen, but I think it's something you can manage. Okay, that's it for this video. Join me again for further vectors and points.